Hey everyone, and welcome to this explainer. I am absolutely thrilled you're here today because we're going to unpack one of the most brilliant architectural secrets in modern computing. Seriously, it's a concept that completely revolutionized how our machines operate. It acts almost like this master illusionist working tirelessly right behind the screen you're looking at. We are talking about the absolute magic of virtual memory.
Okay, so let's jump right in with a paradox. Something that happens on your devices literally every single day. And it brings us to the very first critical question we've got to answer to really master this topic. How exactly does a massive 10 GB video game or some heavy video editing program run perfectly smoothly on a machine that only has, say, 4 GB of physical RAM? I mean, logically, the math just does not add up, right? You can't fit 10 gallons of water into a 4-gallon bucket, and yet your computer pulls this off effortlessly. So how does it do it? Well, that is the exact magic trick we're going to decode for you today.
Here's our roadmap for the explainer. We'll start with the virtual memory illusion, then walk through demand paging step by step. After that, we'll tackle the page replacement dilemma, look at Bilaty's anomaly and algorithms, figure out how we're avoiding the thrashing trap, and finally, wrap up with the real-world impact and future. Let's get right into it.
Part 1. The virtual memory illusion. So our first step is understanding the core deception here, and honestly, I mean that the absolute best way possible. The operating system basically creates this total separation between what a program thinks is available and physical reality. Imagine your computer's hard drive, what we call the backing store, as this massive, multi-story public library. That's where all your information lives. Now your physical memory, your RAM, that is just a really small reading desk. You obviously cannot fit the entire library on your tiny desk. So instead, the OS uses a memory map. It gives the user program this logical memory space, an illusion that it has a massive desk, but in reality, the system is just mapping the specific pages you are actually reading right now onto your physical desk, while leaving the rest of the books safely tucked away in the library.
And that brings us to the actual mechanism making this whole thing possible. It's called demand paging. The golden rule here is that the system brings a page into memory only when it is explicitly needed. It acts as a lazy swapper. Honestly, think of it as the ultimate procrastinator. It never carries a book from the library to the desk unless it is absolutely forced to. What this means is far fewer unnecessary input-output operations, significantly less memory needed right when you launch an app, and way faster response times. But what happens when you try to turn to a page that isn't on your desk yet?
Part 2. Demand paging step by step.
Because you see, when a program asks for a page that isn't currently sitting in physical memory, the illusion is momentarily broken. The operating system has to scramble to fix it. We call this a page fault. Let's walk through this step by step, almost like we're learning a perfectly choreographed dance. Step 1. The program makes an invalid reference, which causes a trap to the OS. It's basically yelling, "Hey, I need this page and it's missing." Okay, step 2. The OS hits pause and searches the physical memory for an empty slot. We call that a free frame. Step 3. It reaches back into the backing store and swaps the needed page right into that frame. Step 4. It updates its memory maps, resetting the page tables to essentially say, okay, crisis averted, the page is here now and valid. And finally, step 5, it seamlessly restarts the exact instruction that caused the pause in the first place. To the program, it feels like absolutely nothing ever happened.
Tracing the whole cycle, you can really see how the initial reference fails at step 1. Then the hardware traps to the OS at step 2. The OS pulls the missing data from the backing store at step 3, drops it right into physical memory for step 4, resets the page table for step 5, and just restarts the instruction. It is a total masterpiece of microsecond-level coordination. But wait, there is a catch here, and the stakes, they are incredibly high. Consider the number 40. According to the performance math from our sources, if just 1 out of every 1,000 memory accesses causes a page fault, the effective access time of your entire system slows down by a massive factor of 40 times slower. So the crucial takeaway here is that while this lazy swapping magic trick is totally brilliant, it is astronomically expensive when it comes to time. The OS absolutely must keep page faults to a bare minimum, otherwise your computer is going to grind to a complete halt.
Part 3. The page replacement dilemma.
You see, the easy part is grabbing a new book when your desk is perfectly empty. But what happens when your physical desk is 100% full and you absolutely need to bring in a new page? Well, somebody has to get kicked off. The system has to choose a victim frame. And there is actually a pretty massive debate in system design about how to handle this. Looking across our sources, there are essentially 2 distinct camps: local versus global replacement. Some designers advocate for local replacement. This is where a program can only kick out its own pages.
It guarantees highly stable, consistent performance for that specific program, but the downside is it can leave your overall memory totally underutilized. On the flip side, other system designers argue global replacement is vastly superior. This lets a program actually steal a frame from another program. Now, while this can make execution times vary wildly, since your frames might get stolen at any moment, it results in much greater overall system throughput. Because of that higher total efficiency, global replacement largely wins out in modern architecture. But hey, regardless of who you steal from, you still have to decide which specific page to throw out.
Part 4. Bilottti's Anomaly and Algorithms.
Choosing that victim requires some pretty deep mathematical strategy. And this leads us to our next essential question. How does a computer actually predict the future to know which page you aren't going to need? Well, it needs a page replacement algorithm, or a PRA. Two incredibly common strategies here are FIFO and LRU. FIFO stands for first in, first out. It is super simple. You just kick out the oldest page that was brought in. But simple isn't always smart. Think about it. A page you brought in a long time ago might be the exact one you are constantly referencing. That's where LRU comes in. LRU stands for least recently used. Instead of looking at when the page was loaded, LRU looks backward in time to see when the page was last touched. It kicks out the page that hasn't been used for the longest period of time. Now, LRU is significantly smarter, for sure, but it's way harder to implement because the hardware actually has to maintain a clock or a stack to track every single page reference in real time.
Now, basic logic dictates that if you give a system more physical memory, more frames, the number of page faults should naturally go down, right? I mean, as the number of frames goes up, the curve of page faults gracefully swoops down. A bigger disk means less swapping. That is the standard, totally expected behavior. But here is a truly surprising, counterintuitive insight. With simpler algorithms like FIFO, you can encounter something called Bilottti's anomaly. It turns out, giving a computer more memory can actually cause it to have more page faults, actively degrading performance. I know, it completely defies common sense. Why does this happen? Well, it's because FIFO is not what computer scientists call a stack algorithm. It lacks the inclusion property, which basically means the set of pages loaded in a 3-frame memory isn't necessarily a subset of the pages in a 4-frame memory. It's this fascinating little quirk of computer science that proves how you manage your space is sometimes far more important than how much space you actually have. LRU, thankfully, is a true stack algorithm, so it avoids this anomaly entirely.
Part 5. Avoiding the thrashing trap.
But even with the absolute best algorithms, things can still go catastrophically wrong. And that brings us to the ultimate disaster state for an operating system: thrashing. Thrashing is defined as a state where a process is spending way more time busy swapping pages in and out of the backing store than it is actually executing instructions. The illusion completely shatters. The system is essentially panicking, right? It gets stuck in this endless loop of page faults because there simply isn't enough physical memory to hold the active pages it needs at that exact second.
You'll see this massive, steep cliff in system performance. As you add more programs to the system, increasing the multi-programming, CPU utilization goes up. The system is humming along efficiently, but suddenly you cross this invisible threshold. The system tries to do too much. The memory fills up, page faults start cascading, and CPU productivity violently crashes down to near zero. The computer is doing massive amounts of work shuffling data back and forth, but it is accomplishing absolutely nothing.
So how do we fix this? The sources introduced an incredibly clever framework called the working set model. Think of the working set model as a super observant librarian tracking exactly which stack of books you are actively flipping between, ensuring you never have more active books than you have desk space. It relies on the locality model, which is based on the realization that programs don't use all their data randomly. Instead, they tend to focus on specific localities or clusters of data at any given time. The working set model uses a moving window, a fixed number of recent page references, to track exactly what a program's active locality is right now. If the total demand for all these active working sets exceeds the available physical frames, the OS doesn't try to just push through it. Instead, its policy is to literally hit pause and suspend one of the processes entirely. It frees up frames to stop the thrashing in its tracks. It's a brutal approach, but it is highly effective.
Part 6. Real-world impact and future. So, how does all this heavy academic theory actually manifest inside the devices sitting right in front of you today? Well, modern operating systems handle this brilliantly using page fault frequency dynamic adjustment. Your device is constantly monitoring the heartbeat of its memory. It establishes an upper bound and a lower bound for page faults. If an app starts faulting too much and crosses that upper limit, the OS dynamically gives it more frames. If it drops below the lower limit, the OS quietly takes frames away to use somewhere else. It is literally breathing, shifting, and reallocating resources on the fly to keep your experience completely seamless. But where is all this going next? An open question in modern computing right now is how virtual memory adapts as we move toward cloud-based computing and unified memory architectures, like Apple's M-series chips. As processing and storage become hyper-integrated, will the line between RAM and storage blur entirely? It's a fascinating frontier.
Which leaves us with this final thought. Think about what your device is doing right at this very second. Just to let you watch this explainer, your operating system is actively juggling memory maps, catching traps, evaluating LRU stack algorithms, preventing thrashing, and swapping data from your storage to your RAM in fractions of a microsecond. That massive 10-gigabyte program fits perfectly into your 4-gigabyte RAM because your computer is the ultimate, highly efficient illusionist. I really hope this deep dive into the magic of virtual memory changes how you look at the screen in front of you. Thank you so much for joining me. Keep learning, and I'll catch you on the next explainer.